Hello, today we're going to tackle a tough problem which is very often used in solutions where people, and I probably have as well, just stop and say, well, this is the Basel problem and well, this is just equal to pi squared over 6. So yeah, spoilers here, it is equal to pi squared over 6. It's a very famous problem, has loads of proofs, and it's quite tough to prove. Most proofs are using some fairly high level maths. But I'm going to try and present a very simple proof. Maybe let's get right into it. And we're going to start off by using a fact that a lot of these proofs actually use, which is the fact that sine of x is equal to x times 1 minus x squared divided by pi squared. Now, although this is fairly well known, especially if you've seen a bunch of these proofs, I'm still going to present a reasoning for why this is true. Of course, not a closed proof. If you do understand why this is the case, of course, just skip this following part. Okay, so we all know sine of x. Sine of x is equal to 0 when x is equal to 0, when x is equal to pi, 2 pi, minus pi, and so on and so forth, right? So we know this function quite well. We know all of its infinite zeros are just on the integer multiples of pi, right? Now we also know something about polynomials, right? We know that if we were to factor them, we could get their zeros easily. And so we could also build a function by just multiplying by the right factor to get a zero. So for example, if you were to have this parabola, we can see that it has the first two zeros sine of x also has, right? So it's obvious that this function is equal to 0 in x is equal to 0, and of course if we plug in pi, we get pi minus pi, which is equal to 0. And so we can build functions this way. We could also just multiply by 2 pi minus x, and so on and so forth. So let's do that for a couple more factors. So again, it has the same zeros as sine of x, which is quite nice. But of course, this function is very different from sine of x. The first problem we have is that sine of x also has negative value zeros. So minus pi, minus 2 pi, and so forth. We can easily fix that by just multiplying by pi plus x and 2 pi plus x. So now we have this function, right? And we're just going to apply difference of squares to simplify our formula slightly. But now there's this other massive issue, right? We can see that this function explodes everywhere except for the zeros. And of course it should, because we're just multiplying by these massive numbers times pi squared. We can keep the zeros in a function easily and still divide by some constant, right? So let's maybe do that. So our f of x was wrong, but what if we were to divide each factor by its constant term? So when we get an infinite amount of factors multiplying, basically all of them will be equal to 1, since the x squared is going to get divided by a bigger and bigger number. So in total, we're just going to get a large product of 1's multiplying together. So it's important to keep this function small, of course keeping our zeros. So notice that each factor was divided by pi squared by 4 pi squared and so on and so forth. And of course this is not a proof, but it's a nice visual representation of what's going on. So this is like 100 factors, 1,000, and this is 10,000. So it basically converges, or it looks like it converges. Of course, this isn't a proof for convergence. It just is a nice visual explanation of what we're doing, right? I hope that's clear. And if you want to know more about this subject, it's called Weierstrass factorization, and it's really quite interesting. Okay, so accepting that this is a true fact, we can now go and use this. So I'll rewrite it slightly such that we can get a slightly cleaner and shorter notation. So we're going to use the product notation, which looks like a big pi, and it's basically the same thing as a sum, but it multiplies stuff, right, as expected. So we're going from n equals 1 up to infinity, and we're going to multiply 1 minus x squared divided by n times pi squared. Okay, so basically all we're doing there is we're multiplying all of these cases for n, so n equals 1, n equals 2, and so on and so forth, and we're getting our product. Okay, now what we're going to do is we're going to take the log of both parts of the equation here. So we're going to get log of sine of x is equal to the log of x times our product from n equals 1 up to infinity of 1 minus x squared divided by n times pi squared. Now what we'll do right now is we're going to combine these two terms. So we're going to get n squared pi squared minus x squared all over n squared times pi squared. Now we're going to use a very important fact, which is that log of a times b is equal to log of a plus log of b, which is of course very well known. Those are basic log rules, and we're going to use that here in a slightly more special way. We can use this rule to just transform this product into a sum. So we're going to get that log of sine of x is equal to log of x plus the sum from n equals 1 up to infinity of the logs of n squared times pi squared minus x squared divided by n squared times pi squared. And maybe think about why this is true for a second here. Of course, it's just using this rule over here. Now, before we do anything else, I'm just going to quickly rewrite this, and we're going to get log of x plus the sum from n equals 1 up to infinity of log of n squared pi squared minus x squared minus log of n squared pi squared. So those are fairly basic log rules, and it just helps to simplify in our next step, which is going to be to take the derivative from both sides of this equation. So on the left hand side, we're just going to have 1 over sine of x, because that's the derivative of log of x, and then times the derivative of sine of x, which is of course cosine of x. So using the chain rule there. So we're going to get cosine of x divided by sine of x is equal to, and now we're going to take the derivative of log of x, which is 1 over x. And next up, we have to take the derivative of each term separately. But notice that, of course, this here is constant all the time. So we're going to get plus the sum from n equals 1 up to infinity of 1 over n squared times pi squared minus x squared, and of course, applying the chain rule, we're going to get minus 2x. Of course, cosine of x over sine of x is going to equal cotangent of x. Now, we'll move this 1 over x over to the other side of this equation, which is going to give us minus 1 over x is equal to our sum. And of course, now we're going to multiply by, we're going to divide by minus 2x, which is going to give us, let's see, cotangent of x divided by minus 2x plus 1 over 2x squared is equal to the sum from n equals 1 up to infinity of 1 over n squared pi squared minus x squared. Now before we do anything, we're going to combine these two terms, which is going to give us, let's see, we multiply by minus x, which is going to give us 2x squared minus x. Let's just combine all of it. And actually, we're almost done with the proof. The next step is just basically the final key to this problem. What we're going to do is we're going to evaluate both sides of this equation on a specific value for x, and maybe you'll be able to guess that that value is x equals 0. But notice that on the left hand side over there, we're going to have to take a limit. Why is that? Because we're going to have 0 times cotangent of 0, which is infinity. So we're going to have to deal with some limits over there. So let's see what this actually looks like. We're going to get the limit when x approaches 0 of 1 minus x times cotangent of x divided by 2x squared. And that should be equal to the sum from n equals 1 up to infinity of 1 over n squared times pi squared. Now, rewriting this first part of the equation, by multiplying both the denominator and the numerator by sine of x, we can actually get the limit as x approaches 0 of sine of x minus cosine, or x times cosine of x, divided by 2x squared sine of x. And now, of course, at this point, we're going to have 0 over 0, since sine of x is equal to 0 when x approaches 0. And of course, if you multiply cosine of 0 by 0, we get 0. And in the denominator, same story, it's even more 0 over there. So let's see what we can do. We can apply L'Hopital's rule because we have this 0 over 0 situation. So we're going to get the sum from n equals 1 up to infinity of 1 over n squared is equal to pi squared times the limit as x approaches 0 of cosine of x, which is of course the derivative of sine of x, minus cosine of x, applying the product rule for derivatives, minus minus, which gives us a plus, x times sine of x. Now in the denominator we're going to get 4 times x times sine of x, which is the first term, plus 2x squared times cosine of x. And now of course at this point we can scratch these cosines of x's. We can also divide by x, and now again we have a 0 over 0 situation. So applying L'Hopital's rule again, we're going to get pi squared times the limit as x approaches 0 of cosine of x divided by 4 times cosine of x plus 2 times cosine of x, since we have to apply the product rule, and then of course minus 2x times sine of x. And look at that. Of course, now we don't actually have a false limit anymore. First of all, if you plug x equals 0 into cosine, we just get 1, so that helps out a lot here, and we're going to get that the sum from n equals 1 up to infinity of 1 over n squared is equal to pi squared times 1 over 4 plus 2 plus 0, which gives us pi squared over 6. So again, I thought this proof was fairly short. We didn't actually have to use any sort of fancy integrals, mainly knowing how to take limits and taking derivatives, nothing more complicated than that. So thank you so much for watching. I hope you enjoyed. Till next time.